Hello, and welcome back from lunch. I hope you're enjoying the food here. I think it's quite good. I know there's a sea of chairs and not so many people to populate the chairs not because this isn't important. This is very important. This is prospecting business pitches, so super important, and it's going to be chaired by the wonderful Abigail from ESRIC, Abigail CALZADA DIAZ. I didn't say it in the proper Spanish way, but I'll stick with Abigail, which I think I can manage. So Abigail's going to chair the pitches over the next hour, and so we want lots of energy in the room. And therefore, as always, I know it's dull, but if you wouldn't mind moving closer, if that's possible for you, to the front row, because really, as a few people have mentioned, the lights are quite strong. And if there is time, Abigail will be able to take one or two questions from the audience, but you can only take questions if she can see you. And sometimes they dampen the lights in the room, but if they don't dampen, thank you everybody, thank you so much. If they don't dampen the lights in the room, then it will look to the pitchees, if that's a word, that they are not talking to anybody in front of them. So thank you for making your presence known. Abigail, over to you.
Hello everybody. I hope that you have a really nice lunch. So I'm presenting, and today we start with the prospecting business pitches. I just want to remind that each of the business pitch have 5 minutes. Maybe we have some time for one question, quick question. But before starting the business pitches, I want to welcome to the stage to Carlos Espejel, that he's going to give us a talk about Helium 3. And in this case, he has 10 minutes, and we will have some time also for questions. So welcome, Carlos Espejel. Suerte.
Thank you, Abby, for the introduction. So I have 10 minutes, and I hope everyone enjoyed lunch. Good afternoon. And it seems I am the lucky first one to be the first presentation after lunch. But you know what? I really think this is maybe the perfect time and the best time to learn about cut-off grades applied to helium-3. So let's get into it. But before that, I would like to share with you about, if this works. There we go. About who we are in SpaceRS. So we are a Luxembourgish company that does resource intelligence and technology. We were founded in 2024, and among the team, we have more than 24 years experience in the terrestrial mining industry and more than 27 years in the space industry. Now, we have 2 verticals, and the first one is engineering consultancy, and mainly applied to the mining industry. And to be honest with you, that's where we have most of our work, and that's what's paying the bills at the moment. The second vertical is technology, and we have 2 main activities there. One, we are developing software for strategic mine planning, and we're happy to say that it's going to roll out in July this year. Now, the second one is we are developing, well, if everything goes well, we should be starting to develop an operational intelligence platform, which is directed to the mining industry, to governments, and to defense. But hopefully, we can tell you more about it next year. So how do we add value to our customers with these services? So we do it through 3 different ways. The first one is through cut-off grade analysis and value chain optimization. The second one is reserves evaluation, and the third one, resource intelligence. And hopefully, we can tell you more about it later next year. Now, for today's chat, we're going to focus on cut-off grade analysis. Now, this is an industry standard. This is used every day. And what I would like to share with you today is how we can use this on the ISRU ecosystem, and specifically applied to helium-3. Okay, we are a very young company, but we are happy to share that we have some relevant, important customers as Glencore and Antamina. And Antamina is one of the biggest copper open pit mines in the world. At the same time, we are about to start a project with ESA, of course, on value chain optimization. And I would love to share with you a picture of one of our clients. This is one of the biggest open pits in the world. It's in Peru. And we're doing, of course, cut-off-grade optimization. And more specifically, what we do is we estimate reserves, we estimate the value of the operation, we estimate the optimum destination of the materials, we can estimate when the mine has to close, and we can also estimate the optimum capacities for extraction and processing. So without exaggeration, this can add value in the hundreds of thousands of dollars. OK, let's go straight into cut-off grades. But still, some of you might be asking yourselves, why do I need to know about cut-off grades? I mean, I can see mining engineers are excited about it, but why, right? And if we can summarize it into one simple thing, is we need cut-off grades to estimate the famous reserves. But let's take one step back. How do we estimate reserves? We need two ingredients. The first one is measured and indicated resources, and two, the economic side of it. Now, to estimate the economic side of it, we need cut-off grades, which estimate the units of cut-off grade, which happens to be ore, which is the economically extractable part of resources. And to estimate cut-off grades, we need the value chain. OK, but Carlos, how do we estimate measured and indicated resources? So for that, I would like to give you a practical example. And for that, I'm going to use this table, this classification system that some of you have maybe seen already. And it's used to report exploration results. It's very simple to use. At the bottom of the pyramid is very low geological confidence for mining purposes. And at the top of the pyramid is very high geological confidence for mining purposes. But let's look at an example. We're on the south pole of the moon, and we have our famous LRO that gave us really, really good data. But for mining purposes, we are in speculative resources. Then let's look at El Cross. It gave us spectacular data. We had an impactor in Cabellos. But that for mining purposes, we're in prospective resources. And it is not until we go there with a lander, and we drill and take some ground truth, that we go into inferred resources. And if we keep exploring on that region, like a lot of exploration, then we can go to measured resources. And it is until then that we will find out that there is a distribution of concentrations of whatever you're looking for: hydrogen, oxygen, titanium, helium-3, and so on. Carlos, do we have reserves? No, not yet. Remember, reserves are made of measured and indicated resources and the economics of it, where we need cut-off grade to estimate ore, and we need the value chain. Simple, right? OK, I think we're ready to go into cut-off grades for helium-3. For this, I would like to show you two types of operations. I would like to show, we're going to assume we are in the Mare, same region, same regolith, but two different types of mining operations. The first strategy is a mine that is only mining for helium-3. The second strategy is a mine that is mining for liquid oxygen and helium-3 as a byproduct. Two different strategies. So we have two operations, two cut-off grade strategies. But before I jump, I want to do a disclaimer. So what I want to show you is not really to say, look, this is better than the other one, but it's to show you how we use cut-off grade analysis to look at different mining strategies and then to find the optimum mining strategy. And that's what we do in mining all the time. OK, let's look at case A. On case A, on this value chain, we are assuming for extraction a mobile bucket wheel excavator, for processing a reactor at 700 degrees, and of course, isotope separation. And for market, we're assuming that we're bringing back the helium-3 for quantum and fusion. And in terms of some assumptions, we're assuming the famous 20 million per kilogram of helium-3. And we're going to assume a throughput of 670,000 tons. What we're going to try to answer here is what's the minimum helium concentration for this mine to be profitable. OK, let's look at the second case. Case B is a liquid oxygen operation, where in our assumptions, we have a bucket drum loader like the NASA Razor for processing a reactor at 900 degrees. And in the markets, we're assuming that we're going to sell the liquid oxygen on the moon, and we're going to take the helium back to Earth. OK, and in the assumptions, they're going to pay us $2,500 per kilogram of liquid oxygen. So let's And of course, what we're going to try to answer here is what's the minimum concentration of oxygen to have a profitable operation. So let's look at the first case A, which is for a helium-3 mine. Let's look at the first line. It's very simple. So on the left-hand side, we have a concentration of helium of 1 ppb. And according to the cut of grade equations, we would have a minus $3,000 per ton. So of course, 1 ppb is uneconomic. Then if we go to the 11.8 of one of the Apollo 11 samples, very uneconomic. If we use the famous 20 ppb, very uneconomic. But if we go all the way until 316 ppb, that's where we break even. So anything above that, it's profitable. So in this scenario, our cut of grade, or break-even cut of grade is telling us that it's 316 ppb, and that's where the reserves are. So our reserves would be with anything above 316. So we can do a lot of analysis now. The first one is, in terms of exploration, we would need to find a unicorn deposit with a minimum concentration of 316 ppb. Or we need a market price of not 20 million per kilogram, but maybe 80 million per kilogram. Or we need to look completely at our technologies to make them more efficient. Let's look at the next case. So this is our liquid oxygen operation. And let's look at the first line. It's simple. On the left-hand side, we have the oxygen concentration that can be recoverable with hydrogen reduction within a 1% ilmenite in regolith. That would give us minus $3,000 per ton according to cut of grade. And then we're assuming a helium-3 ppb of 1 to 2%, and that will add up to $22 per ton. Okay, now let's look at the cut of grade analysis. So if we look at the different cut of grades, we'll see that it is only until 8.1% ilmenite that we become profitable. And what I would like for you to see here is that we add some credits of up to $174 per ton. So if we keep going, of course, it's profitable. And what we can see here is that if we find a deposit with a minimum concentration of 8.1 concentration of ilmenite, it starts becoming profitable. And something else that I want you to see here is that the helium-3 is adding some valuable credits. And this is exactly what we do in the mining industry. I just would like to end with one last slide, a fun slide. Sorry, and the reserves are, of course, after 8.1. So I would like to end with this. So if we have different cut of grades, we also have different scales of mining. So if we start mining at a cut of grade of 11.8 ppbs, to produce 1 kilogram of helium-3, we will need to mine 113,000 tons. And just because we're in Europe, I would like to give you a European example. We will need to mine around 11 Eiffel Towers in terms of mass to get 1 kilogram of helium. Now, if we mine at a cut of grade of 20 ppb, we would need to mine around 7 Eiffel Towers. Now, if we then go for the cut of grade of around 316 ppb, which is our break-even, we would need to only mine half an Eiffel Tower. So the learning here is that depending on your cut of grade, it will affect directly in your scale of mining. And with that, I would like to finish and just end up with a question: what is your cut of grade? Thank you.
Thank you, Carlos, for the interesting presentation. So I want to ask the audience if there is any questions that I'm really sure they are for Carlos. So please show. Oh, yeah, there is a question there.
Hi, Miguel Albino, in the University of Lisbon. So you considered helium-3 as basically to add value to the operation as a byproduct. But mining contracts also have penalizers, and that can devalue the operation, raise the cutoff grade. How do you envision that the add up for certain operations of these penalizers, like the penalties, could affect the cutoff grades and make this operation economically more complicated?
So that's an excellent question. So in the mining industry, within the cut-off grade equation, we have one variable which is called the realization cost, which is where you put your penalties. You put your credits and your penalties. And then when you're doing the optimization, those credits are taken into account. Now, in this initial model, we didn't take into account any penalizations like arsenic in the world of gold in mining. But we have an initial model, and if you would like to test any of those like penalties or variables, feel more than free to come and ask. And yeah.
Thank you. Thank you.
There is any other question? Yeah, Clive in the front. Thanks.
Clive Neal, University of Notre Dame. Carlos, the 316 ppb helium-3 may cause a little consternation based upon Apollo data, but I think the savior for this is the fact that you've got mature regolith, and what we got with Apollo is that's a minimum value for mature regolith, because these are implanted and they've been transported, they've been sampled on the moon, most of them not in a vacuum sealed vessel. They've then been transported off the moon back to Earth, and there's been a loss there. One piece of data that is needed, and I'd like your thoughts on this, is if we go to the moon and get the true value of mature regolith, do you think that would be a game changer, or do you think that we didn't lose that much helium during the sampling and the transport? So getting the actual value of solar wind in mature regolith is what I think would really inform your model a lot more than freaking everybody out with 316 ppm.
Yeah, no, I mean, there's a number of really good points there. I mean, the first one, of course, there's no deposit with 316 ppb. But the math would tell us that we would need to find, with the current assumptions, a deposit that has 316 ppb, but it's not possible. So that's obliging us to then increase the market price or improve our technology, right? So you have those two options. But in terms of the certainty of your data, we need to do plenty of exploration. And as I was mentioning before we can even go into reserves, we need to get to measure and indicated resources.
Okay. Unfortunately, we don't have more time for questions. Thank you, Carlos.
Thank you.
Really nice presentation, as always. Okay. Now we are actually going to start with the business pitches for prospecting companies. So I would like to start and give a welcome to Boris Petrovic from ISRU.ai that is going to talk about agentic simulations of autonomous lunar ISRU operations. Welcome, Boris.
Thank you, Abigail. My name is Boris Petrovic. I own a small development studio named ExoTesla, which specializes in simulation environments, digital twin development, and immersive realities. So I developed this agentic AI system named ISRU, which focuses on autonomous ISRU operations, which is planning to simulate various types of scenarios of ISRU operations, and I will talk a little bit more. There is unfortunately no time to detail everything. So this platform uses a specified space geographic information system developed by ExoTesla, which is an API that serves particular mapping data to the agentic AI system. Here we have a global mapping interface that relies on data from, at least here shown in as a lunar map, NASA Lunar Reconnaissance Orbiter, and for the minerals, the JAXA Kaguya system. Here we can see some captures from the agentic AI output that relies on the orthophotos of the Lunar Reconnaissance Orbiter, the LoLa elevation, digital elevation models, and the whole movement of the agentic AI system is programmed through a kind of a slope modeling. This scene is located in the south pole of the moon, You can see in the blue parts are the PSRs, which are the targets for the ISRU AI agents, which are of various flavors. The agentic AI system is developed on the data of a couple of thousands of research articles. So all of these were fed into the system, and all of the data models of ISRU AI are based on probably some of your articles as well. So it's impossible to flee from the future of agentic AI. So up to 32 specialized AI engineering agents were used to extract interesting locations and processes to model ISRU agents. And the scenarios that were developed with this data are located on the Moon, on Mars, and on small bodies. So in these particular demonstrations, I used 30 scenarios, 30 lunar scenarios, 30 Martian scenarios, and 30 small body scenarios. So the algorithms presented are swarm coordination models in between the various flavors of agents. They use energy-aware pathfinding system. And there is obviously an idea to component this with hardware robotics. And here we have a gaming model of a production of LOX that focuses on the collaboration in between the agentic AI robotic operated vehicles, processors, howlers, excavators, and even an ISRU processing plant, and in the future, some kind of additive manufacturing facilities and construction. This can all be modeled through agentic AI. So the lunar scenarios compose of 5 of assessment, 5 of acquisition, 5 of processing, production, construction, and integration. Here we have a map of the path traversals. We use a kind of a hexagonal coordination system. And the whole ExoTesla space geographic information system divided the Moon in such a coordination system. Otherwise, we focus also on the Marius Hills location, and in the video that we will play during the questions, there will be a live show of how the system operates. And the system is just one component away from live operation, from simulation that is intended to be useful for mission planning and development. So the idea of ISRU is really to become a kind of one-stop shop for training of AI models. So we want to develop a physical location for training of robotic systems. And this also is a part of the business model. So software as a service, data as commerce, and models as validation as well. Maybe we can see the video.
I think we are running a little bit out of time.
So, for the questions.
There is a quick question. Oh my God, with the light, I cannot see anything. Well, I'm really sure questions will raise up, and we have to keep going. So if you have any questions to any of the presenters and you don't have time to say it here, please go and contact them and talk to them directly. Thank you, Boris.
Thank you
very much. Okay, next we have Jiang from Amelia Space Technologies that is going to talk about lunar intelligence. Welcome, Alan.
Good afternoon. I'm Alan Jiang, founder of Amelia Space. I attended the Space Resources Professionals course this weekend, and I highly recommend it. The content was out of this world. I was planning to tell a space-related joke that I learned from the course, but I was a bit worried that the joke wouldn't land. But I can share with you one key takeaway that I have personally gained from taking this course, and that is in the space resources value chain, we as a community, as an industry, are here in the very early stages of prospecting and exploring. And the capabilities of remote sensing, of sampling and measuring, and data solutions will help drive us forward into space resource utilization. However, as we know, that the challenge in this context is not necessarily more data or higher quality of data, although that will help. The challenge is more in the integration and the interpretation of all of this data, which makes sense as a challenge area, because ever since we've been going to the moon, there are hundreds of scientific instruments collecting different diverse pieces of data, but they're not talking to each other. If only there was some type of gravitational well that could ingest all this data, harmonize it, analyze it, and enable developers and researchers to advance our understanding of the lunar surface. This is what we've been building towards at Amelia Space. We call it a planetary intelligence platform. And I'll show you the demo, a sneak peek of it now. This is the platform. And now let's go to the moon. Take me to the moon. Now we'll fly towards this beautiful celestial body, and we can ask it things like, okay, show me where all the water ice is. Now it's moving towards the lunar south pole. Let's see what it does. Now it's analyzing the permanently shaded regions, integrating hydrogen data sets, and it's overlapping them in this area. And now it's saying that the Shackleton region is a good candidate. All right, now what if we want to ask a better question? What if we want to build a habitat around this area? Where are those best locations and why? It's a good question, it says. It wants to come. All right, so now it'll go through and analyze all the available data, looking at illumination. Now it'll look through the slope and analyze and assess the data sets that we have here. Now it's going through and analyzing thermal stability. And now we have, what does that say? Surface roughness, the smoothness. Now we're looking at the permanently shadowed regions. And it's saying that the hydrogen data for this is not available, so it's keeping us honest about what our data gaps are. Now it's synthesizing all this information to give us the top candidate sites. This, of course, needs to be validated and tested and measured. But it's giving us these three areas, and it's ranking them across the criteria that we care about. And it's saying that if we want to learn more, we can dig in. I'm not sure if that was an intentional pun. So our platform matches to adapt your mission through a decision-making framework. Essentially, every mission can use the same data, but come out with a different output based on its objectives. What we aim is that this platform allows us to answer better questions. For example, where is the most accessible water ice, the easiest access water ice? Where should we build the telecom stations around the lunar south pole? Or even, what kind of data are we missing that would make a meaningful difference to our decisions? So to conclude, the reason I'm here is to work with you all, and this is how we can work together. If you're a space agency or a space company looking at site selection, landing feasibility, we can work together. If you're a researcher that wants to publish your lunar research and reach a wider audience, we can work together. If you are part of the lunar community trying to solve the coordination problem and trying to work towards a shared standard and framework, we can certainly work together to go to the moon and to build a more peaceful, sustainable, and equitable space civilization. Here's my contact information, my email, and my website. I hope we can get in contact, and I look forward to speaking with you soon. Thank you.
Thank you. Thank you. Let's see if there is any quick question. Yeah, there is one question back there. There, yeah. Thank you.
Thank you for your presentation. Sattar from Cardenas Technical University. Could you please tell me which large language model you use for your platform? And also, did you verify the answer you received from your large language model? For example, did you use ChatGPT or Gemini, or which platform did you use?
We build upon what works, so we kind of have a custom way of doing it. The language model does not do scientific analysis, so we create that trust boundary. All the scientific data is done through data science models. The language model rather orchestrates and synthesizes that information back to make it more accessible.
Okay, thank you. We don't have time for more questions. And yeah, if you have more questions, please reach Alan outside at any time. Thank you. Thank you. Now, I would like to invite to the stage Eric Sundby by TerraSpace, that is going to talk about subsurface resources intelligence and at speed and scale. Welcome.
Good afternoon. My name is Eric Sundby. I'm the co-founder and CEO of TerraSpace, where we provide subsurface resource intelligence at speed and scale. The challenge that we address as a company, particularly terrestrially, has been around for quite some time, and that's the issue of dealing with a lot of the core samples that come out of the ground and are shipped off to mineral analysis labs in the exploration and mine planning process in mines across the world. That process really has not changed over decades. You still see a lot of these core samples be taken, transported, sometimes hours, if not multiple days away from the site to be able to be tested. And then, due to a lot of human oversight and laborious processes, you generally have to wait, possibly even months, to get your results back. Now, not the same problem, but parallel in space is just a general lack of subsurface knowledge. We do know a lot about the lunar environment, but there's still much to be learned. And so for TerraSpace, our solution is pretty straightforward. We take a multitude of commercially accepted and tested sensors off the shelf, and then we connect those with our proprietary machine learning technology that enables us to get essentially a full spectrum analysis, fuse that data from those various sensors, and then analyze them, providing those outputs and reports to our mining customers. And as you can see here, there's a little bit of our visualization capabilities that were used in a recent project at a mine in Chile. We also have the ability to do interpretive analysis using our models across various samples and borehole samples, allowing for the mine industry to be able to get that ore body knowledge for their mine planning. Now, the opportunity, particularly terrestrially, is quite large. These mineral analyses are conducted across mines everywhere, and generally within North America, about 20% of these mines tend to look into newer technologies and innovative methods. And so for us, we're targeting those in the industry. A handful of those that we've signed agreements with include Rio Tinto's Resolution Copper, American Gilsonite Company, Chilean Cobalt, and a few others. And so that allows us to break into the mining industry and create a financially sustainable process for ourselves as a company, while we're able to reinvest some of those profits into our initiatives with the Moon and Mars. And that, paralleled with the increasing interest by NASA and the CLIPS missions, as well as other space agencies such as ESA, allow us opportunities to extend this technology to the lunar surface. So our business model essentially comes from three different areas. First is that if you are a mine and you have already logged or scanned your core, but you haven't necessarily analyzed it, we can actually come in and fill that backlog in with our machine learning capabilities and provide you those outputs and readouts, which is some of the work that we're already doing in the mining sector. The second is being able to forward deploy a capability, essentially our SmartScan platform, to a site And so upon immediate collection of those samples, they can be assayed, and then that information can be provided in a near real-time analysis capability. And then, of course, why we're all here is for space resources, being able to extend this technology for surface and subsurface exploration on rovers and landers enable us to get some of those characterizations that we so need. We wouldn't be able to really do this without any of the partnerships that we've developed, especially across the private and public sectors, and we've been working very closely with institutions such as the Southwest Research Institute, Oak Ridge National Lab, and a few of the geologic surveys such as in Texas and Utah. And we also wouldn't be able to do this without the great team that we've assembled. So we have aerospace engineers to geologists and leaders in AI and machine learning development, as well as the advisory that we have at the company, including Dr. James Riley, who is the former director of the US Geological Survey and NASA astronaut, who's actually here with us this week, as well as Lori Leshin, the former director of NASA's Jet Propulsion Lab. In going forward, really interested in making a lot of connections here and seeing what possibilities exist in potential collaboration, as well as in our current seed raise. Thank you very much.
Thank you. Wait 1 second. Let's see if there is any quick question, please. Yeah, there is one there. Clive.
Thank you. Yeah, Clive Neal again. You're interrogating the subsurface on the moon. How are you doing that?
That would be through cooperating with various partners, particularly in drilling technology. We do not necessarily focus on that. We focus primarily on the analysis and assay. That would include a handful of sensors, being able to collect that data from those samples.
Okay, we don't have time for more questions. This is a very quick session. So I would like to invite to the stage to Brian Kotick from Outer Space AI to talk about a space Earth data intelligence infrastructure. Welcome.
Yes, I'm not Lyric Chilawanzi, as you know. This is actually Lyric's brainchild, and I'm here representing him as a legal and policy advisor for him. I'm not going to go through the slides because I just want to focus on the content, so I hope you can be absorbing what I'm trying to get across here. So Lyric is actually an architecture by trade and was studying architectural design and design engineering, and through his PhD studies was migrating into AI technologies, advanced technologies, and also looking at lunar habitats. And while he was going through his research, he found that he had to go through certain design parameters to understand how this structure would look. So he was looking at whether to build on the surface or subsurface, whether they could build near lava tubes as locations for specific work. There were structural and mechanical factors, of course, material composition, how that would operate in microgravity, and radiation, and then also the human and psychological factors as well as many others. The problem he found, and something that I've heard from another presentation just now, was that the community has a vast amount of data that's being produced, but it is fragmented and underutilized, so I echo those sentiments. So while we're connecting an enormous amount of data, it is not only disconnected from each other, but it's also disconnected from any actionable decision-making, such as science policy, sustainability, and effectively business strategy. So the critical opportunity Lyric and I are exploring is how to transform that existing data into predictive decision-ready intelligence, and that predictive element is something that I want to differentiate Outer Space AI from other companies. So the core idea is called Generative Superintelligence, or GSI. It's a computational infrastructure that connects that space-based data acquisition layer and adds on top of it the AI-driven superintelligence to enable that prediction and planning and optimization, which we see a lot of projects are doing themselves, but actually predicting that outcome before it's even put into action. So the system architecture has 3 layers. The first layer is a data acquisition layer. So of course that comes with the inputs that you've heard from other presentations. You have the Earth observation data, ecosystem data. You have the constellational global satellite navigation data, the satellite communication data, remote sensor capturing, and then when we look towards the moon, the lunar reconnaissance orbiter data. Then that data is then processed, cleaned, geolocated, and time synchronized, and stored in cloud-based data hubs. And that layer then establishes the opportunity to scale these data pipelines as this AI machine learning becomes more advanced. There's talks of not only these AI domain-based systems, which you mentioned, Claude and Gemini, but we're going to go into AGI, which is the artificial general intelligence. And at that point, you're going to have machine learning that doesn't need to be retrained or continue to be trained because they will be making these decisions on their own. And that can then, and this is just speculative at this point, the artificial superintelligence further down the line, where they would be fully autonomous and able to realize problems that we don't even know of yet, and then make those decisions in a predictive sense and operate fully autonomously. For this structure, though, the third layer is going to be the AI intelligence layer, which is the proprietary computational model where it can learn from the historical data and then detect patterns, model complex systems such as the infrastructure that Lyric was looking into, and then predict these future scenarios and quantify these risk analysis and mission optimization strategies. So the output from our model is this GSI actionable intelligence. So it won't be raw data, it won't be static reports, and it won't be simple answers. It's going to be strategic roadmaps and real-time decisions that allow you to have predicted models for planning and policy, decision support tools for business and governments looking into speculative areas or resource extraction that they are not sure whether those minerals exist or to what level they'll be able to extract, real-time situational awareness on actually what's happening right now going on in these areas, both on Earth and on the moon and further afield. And then design recommendations, which is what Leah was looking at in terms of the lunar-based construction and habitat construction. So design recommendations on how to use these materials and how to make sure that they're maximizing energy efficiency and able to have human permanence in those habitats. So the vision for the future is to become this foundational infrastructure for AI space intelligence in this predictive sense, so that it will have terrestrial applications in the short term in the sense that it'll promote, show environmental sustainability, the ability to live in extreme environments and natural disasters, building smart cities and the like, and then extrapolate and learn from that for the outer space applications for lunar bases, Mars habitats, orbital stations, and deep space vehicles. And then in the long term, but also this corresponding undercurrent throughout all of this would be the long-term science, policy, governance, and economic planning, which we hope to have integrated as well. And I think I'll end it there as my time's run out.
Thank you very much, Ryan. I just want to ask if there is any quick question about the audience. Okay, so I think we will move on. If you have any questions, please reach Brian outside at any moment. Thank you. Thank you, Brian. So, I would like to invite the next speaker, that is Miguel Arias from Volcanes, that is going to talk about multi-sensor payload for real-time mineral prospection. Welcome, Miguel.
Hello, everybody. I'm Miguel Arias. I'm the CEO and co-founder of Volcanes, a company incorporated in Paris last year. And I'm going to talk about a multi-sensor payload that we are developing for real-time mineral prospection. So the problem, we already heard several presentations about the problem that we have different kind of maps or sensors that have scanned the moon, that they don't have the same resolution and coherence. But we are focusing on a different approach for this. So instead of trying to merge all those and try to make sense of that is already a very good step, we are developing a multi-sensor platform, a multi-sensor package that has several sensors, and that we are going to make data fusion directly on the edge. So basically, the Vulcanis multi-sensor package is a hyperspectral camera with a LIB sensor and a LiDAR, and for the space case, for the moon, it's going to have a subsurface radar. So with that information, instead of sending all the information back to Earth, because that could be terabytes of data, the idea is to do processing on board with the sensor, a kind of smart sensing device. So with that, we can infer and have certain degree of certainty about what are we finding. Also, the idea of having the sensor is that we can have the scanning at very close distance to the surface, like between 1 meter to 10 meters. So that could be used from rovers to space hoppers. So I'm going to come back to that later. But the general idea is that we can combine two different sensors, and that the, let's say, AI, the Bayesian diffusion engine or other machine learning algorithms can infer and disambiguate things that we are seeing. For the Earth case, of mining Earth case, what we are seeing is that we can separate between silicates from sulfides or oxides, which is already value interest of operations in, for example, in copper mines. And for the moon case, we can disambiguate and have a more certainty, or not only a degree of probability that there's water over there, but a number that we can attach there. And ultimately, we can create a probabilistic mapping of what we are seeing. So that's the actual intelligence that we are developing on board, because we can have like signatures for multi-sensors that can label the things that we are seeing. So all these can be used, and I'm going to skip this one because the idea is to enable mapping from hoppers or microflyers like this for the moon, or balloons on Mars. And that we can do these kind of missions, that we have a hopper that lands somewhere on the moon, and we can send it to scan areas like, for example, 10 square kilometers somewhere, and give enough resolution for sending later a rover. For example, we are targeting to have at least 1 meter per pixel, and could be lower than that, but for the LIBS, the disambiguation is going to be in the order of 1 square meter. So it's an enabler for that. And in order to de-risk that on Earth, we are testing that on the, we are planning a couple of pilots tests at the end of the year on mines on Earth. And actually we discovered a couple of very interesting business cases over there, because we could be mapping and evaluating the ore grade in production mines. So for example, for copper, we discovered that if we can improve the ore grade measurement during operations, a typical medium-sized mine could be saving between $10 and $3 million if we increase only 1%. And typically, we should be able to increase in the order of 3 to 5%. So that's something that we are targeting in our roadmap, because for space it's going to be like 3 to 5 years, but we think that in a year or two, we should be able to have this as a running business on Earth. This is just like a summary of the things I'm saying. We have a couple of mines, one in Mexico and one in Romania with another use case that we are in talks. And this is our funding team. My co-founder, Lutz Richer, has experience with scientific planetary sensing. Adolfo is a serial entrepreneur from Silicon Valley, and Tony is our mining expert in the company. So we're in the pre-seed stage, and we are looking for advisors and alliances, or some synergies that we may have with you. And I'm going to be around for any questions or continue talking about this. Thank you.
Thank you. Well, I see that we have one question right away.
How close does your LIB sensor need to be to a rock face or a mineral face for it to be accurate and useful?
That's a technical question that we are still iterating, but we are targeting to be between 3 to 5 meters from the surface of the rock.
Okay, so we don't have more time for questions right now, but please reach to Miguel if you have any questions of inquiries. So now we move on, and I would like to welcome James Parr from Trillion Technologies. He's going to talk about the lunar foundational models. Welcome, James.
Thanks so much, Abigail. Yeah, it's such a good pleasure to be here, and I'm hoping the slides have come. One of the reasons why I'm chatting here today is I'm privileged to be representing our partnership with LSA and ESRIC. I run FDL, and one of our labs is the Lunar Lab, which, not surprisingly, focuses on lunar exploration. A little bit about us. Very heavy slides, I think. Next, here we go. We decided, again, with our partners at LSA, that it was time for us to build a foundation model for the moon. And I'm not sure in this room if you're really aware of the difference between a digital twin and a foundation model, so I thought I'd just do a very rapid sort of 101. Obviously, machine learning can do amazing things. This is work we did a few years ago, which shows that we can extract the metallic anomalies from the lunar surface. But this is a narrow model. This is a one-off. The goal of a foundation model, of course, is to do something which can be applied to many downstream use cases, including this one. So this is sort of what they look like. They ingest a whole lot of data. They then squeeze it into this enormous embedding space. And then once you have that resource, you can then retask it to lots of different things. As you know, with what's happened with ChatGPT and Claude and these other models, scale matters. The bigger the model, the more effective it is. And we've seen this in the geospatial world, where geospatial foundation models are starting to get bigger and bigger and more effective. Over the last few years, there's been a revolution in text, which we know about, but also vision. And then you'll see at the bottom geospatial models and heliophysics models, which we've been lucky enough to partner with NASA on. And you can see here ChatGPT, which really set the world on fire for text. There hasn't yet been a ChatGPT moment for geospatial or science, but we're hoping that this will happen very soon. And in fact, if you've been following Planet Labs, they've just released their first geospatial foundation model, which could be a GPT moment for science. What's interesting about foundation models as opposed to a digital twin is multimodal. And you can see here they can do things which you'd expect a model to do, segment and classify, but they can also start to understand patterns. So they can understand the functional relationships through time. And this is sort of what makes them sort of special. Because once you have a foundation model that understands, I use that word carefully, understands the data it's looking at, it can start to do science. And so this is sort of the sort of stuff that we have been doing. I'm going to go through this. The model's based on these data sets: optical, thermal, gravity, topographic, and radar. And it's all ingested together into this big latent space, as I mentioned. But then once you have this model, you can do things like, where's the titanium? And so this is what this map is showing. The foundation model is showing that it can understand where the titanium dioxide is on the lunar surface. We also gave the model to some external users, organization called DataRock, and you can see here they've used the model to understand nuances within Sea of Tranquility. On the left-hand side, this is USGS's standard map of the lunar surface. You can see here that the model is able to understand and see nuances that USGS hadn't identified in the past. So this is exciting from a science perspective because the model's showing it can allow us to understand new things about the lunar surface. Come and see us. We've got a stand over by ESRIC, and we can explain a lot about the details of the model and where we are and where we want to take it. Obviously, the business context has been well explained by colleagues. The idea is we can use a model like this to really support a decision support system for the lunar surface, a decision support system that understands science. So Once we have that, we can start using agents to query it. And this is a system which does runtime validation of the query. Sorry, these slides are a little heavy and it's taking a while to go forward. But with that, I'll say thank you very much. Again, appreciate the partnership with our friends and colleagues at Luxembourg Space Agency and ESRIC. And yeah, come and see us. We'd love to talk more about it.
Thank you, James. We have time for one super quick question. And if not, Trillion Technologies have a booth right in front that you are very welcome to visit and hear more. Okay, thank you, James. Finally, our last speaker for this session is Giulia Consuma from the European Space Agency, that I think she has some announcements to make. Welcome, Giulia.
Yeah, hello everyone. My name is Giulia Consuma. I'm a research fellow from the European Space Agency. I'm not going to speak about my research, but I'm just speaking on behalf of the Lunar Science team and the Exploration Science team from the European Space Agency. I'm going to give some announcements and calls and news from our exploration team. One highlight is that we have a new website for the Exploration Science. So I encourage you to scan the QR code or just type that website. You're going to have all the activities that we are doing, from research projects to the missions going on from Moon, Mars, also regarding life science and so on. We have a new logo of Exploration Science that is encompassing all the topics that we are working on, and hopefully you're going to be more and more familiar over time with this. You're going to see that more often. I suggest you also to subscribe to the newsletter. You're going to receive probably a monthly newsletter regarding all the news that we have from the Exploration Science. Okay, one important highlight that is of interest, I think, also to many of your colleagues that are probably outside this room, so please share this news. We have the parabolic flight campaign that is open now, and this is going to be under lunar gravity conditions, so it's very useful also for ISRU experiments, for example. I have a video, and I'm going to let the project coordinator of this parabolic flight campaign to speak about this. Let's see. And the volume doesn't work.
European Space Agency. We've been seeing an increased demand for science and technology in lunar gravity. So I have a special announcement to make. In spring 2027, we're going to have a parabolic flight campaign dedicated to lunar G. 93 parabolas of only moon gravity. We have a few hot topics that the agency really wants to focus on. The effect on humans, neurovestibular changes, sensory motor changes, altered blood flow, this kind of thing. Which exercises might best keep our lunar explorers fit and healthy? We also want to look at the lunar environment. How are we going to characterize aspects such as the abrasive lunar dust, the exosphere, the complex electromagnetics? How are we going to deal with those things for humans and for our technologies? We would welcome experiments on in-situ resource utilization, figuring out how to extract and use the water, volatiles, and minerals in the lunar surface, and on advanced manufacturing techniques so that we can make the tools, spare parts, and even the habitats that we're going to need for humans' increased presence on the moon. But there are also many other topics that we are interested in. For more information and to make your applications, please go to ideas.esa.int and search for our Exploration Science Parabolic Flight channel and our Technology and Commercial Parabolic Flight channel. The deadline is the 15th of June. Then there will be a peer review process where we make our selection over the next couple of months. So we very much look forward to welcoming you on board.
Right. Don't forget about this deadline, 15th of June, and please share this information. And as they said before, these are the eligible teams that we are looking for. So you're very much welcome to submit your proposal. Then another thing, we are going to have some more calls to be published around June 2026, so around in a month. The idea is that we are looking for scientific payloads for more details in terms of what kind of science Everything is going to be published, again, in the Exploration Science website or in the general ESA Human and Robotic Exploration team. In addition to the payloads, we are also doing an extensive work on trying to understand what are the main data gaps within the lunar science context. And in this regard, we're going to publish a request for information on lunar data products for exploration science. So as a CISA, we are really interested in getting more data also from different companies or university or whatever you have. These are the main areas that we are more interested in: landing science assessments, environment and facts, and local resources. So just watch out to the space on the Exploration Science website for this. Last thing, we're going to have the ESA Exploration Science workshop to be held at the Italian Space Agency in Rome at the end of November. We're going to have a lot of all the research fellows showing and presenting their research, as well as our science leads and keynote speakers. So this is going to be a really fun and exciting activity, so you're more than welcome to join us. And again, the more details will be announced soon. And that's mostly it. Just make sure you're subscribing or just looking at the website. Thank you.
Thank you, Giulia. Thank you. So, well, I'm afraid that we have reached the session for today. Don't forget to actually register for the newsletter and visit the new ESA Exploration Science website. Thank you very much to all the speakers, to all the business speeches, and to all of you for being here today. Thank you.
Thank you to Abigail, and I think, Abigail, you can actually sit on the stage even, because you're back up again. The next session is going to be led and chaired by Caroline van der Bogert, who is from the University of Munster. We heard her speak earlier today, and she is also the ESA Integrated Team Member for HRE Lunar Science. So welcome back to the stage, Caroline, and if you want, I can also introduce your panelists. Perhaps you're going to do that yourself. Well, your panelists are Clive Neal, University of Notre Dame. We've got Abigail, ESRIC, back up on the stage. Gary Lai from Interlune. Antonino Salmeri, who is from Lunar Policy Platform, LPP. Heard him speaking yesterday. And Jerry Sanders from ESRIC. Thank you. And thank you, Caroline.
So I would like to welcome everybody now to our panel discussion about challenges and opportunities in resource prospecting. And maybe I'll give everyone an opportunity. We'll just go down the row here. If you could just reintroduce yourself very briefly to the audience, what your name is, of course, we sometimes know, Jerry.
Hi, Jerry Sanders. I work at ESRIC. This is my third day there. Before that, I did happen to work for NASA for 40 years, leading in situ resource utilization for 25.
I'm Gary Lai. I am a co-founder and the Chief Technology Officer of Interlune, which is a commercial company based in the United States, focused on space resource utilization, especially starting with helium-3. And before co-founding the company, I spent about 25 years primarily developing reusable launch vehicles, many years of that at Blue Origin.
Hello, I'm Antonino Salmeri. I'm director of the Lunar Policy Platform. People know me here as the lawyer.
Hello, I'm Abigail CALZADA. I'm senior researcher at ESRIC, and previously I was working as a lunar expert and mission planner at a private company.
Clive Neal, a 40-year lunatic, and I'm passionate about all things about the moon. The moon, not a moon.
So I'm extremely happy to have all of you here on the stage with me so that we can talk about, I'm focusing in on a couple of general topics. Data gaps, that's kind of one of the going themes that we always keep talking about. Data acquisition and sharing, we heard from some of you individually already about the importance of thinking about that and also doing the legal framework for that. And then I want to kind of close up, if we don't go over time, on how are we doing on our progress on prospecting. So I think I'm going to start with sort of a little yeah, a little kind of a trick question. And I'd like each of you to just say which data gap, singular, is most pressing from your perspective. And just give me like a quick 1.5 minute answer. So why don't we start with Clive and we'll work back our way down the panel. One answer, Clive.
One gap.
One gap. What's the most pressing?
Ground truth data.
Ah, clever. That's a very clever answer.
Okay. So I don't want to repeat the ground truth that I think that actually is really important. So I'm going to say structural geophysical data.
Okay.
I'm not a geologist, so I'm going to give you a different answer. Who does what in prospecting?
Okay.
I'm going to give a slightly longer answer, but it is also ground truth data, but obviously for Interloon, for helium-3 specifically, it is ground truth data validating that the theory around the correlation between titanium dioxide and helium-3 survives, goes all the way out to the very highest concentration titanium-rich areas on the moon.
And I'll round it out by basically saying not just ground truth data, but in particular water resources in smaller permanently shadowed craters, because that is critical to understand before we decide where we're going to build our infrastructure.
Okay, so I think you've all realized that the panel here, we're talking not about orbital data per se, we're talking about ground data. So the question that follows that is, what concrete actions are being taken? I mean, this is kind of part of this whole week here, but what's actually preventing us from already this year having some of these ground truth points achieved?
Well, I guess I'll start on this side. So first of all, a tremendous amount of activity is going on. I think what has prevented us up to this point has been some of the failures of the landers themselves. I mean, we had Prime 1 that was aimed at going to volatiles. Viper mission was delayed because of a lander issue. LUPEX, which will look for water ice as well, is semi-delayed based on the Indian ISRO lander being used for something else, sample return, I think. So I've seen tremendous progress in the number of instruments being developed, the number of missions being proposed and trying to have flown already. But I'll leave it to my colleagues to say why that hasn't panned out yet.
You can go in this direction.
Yeah, or Clive is grinning. Would you like to jump in, Clive? Okay.
Okay, well, first off, you asked us to name just one,
Right.
which is very hard to do. I don't want to, there is a very high importance on the orbital data as well, but the ground truth data is really a means to calibrate and prove that the orbital data is real, because it is obviously much more effective to build a very comprehensive map of resources from orbit. You just need to have data points that you can anchor it to on the ground. In terms of what's limiting, I do agree there's a lot. We're on the verge, and maybe it seems like we've been on the verge for several years of a lot of activity happening, but that is about to explode. Certainly, Interloon, in order to get that ground truth data, we are having to design our own payload to pay for a lander to go over to a very specific location, the highest helium-3 area on the moon, which is a financial and business risk as well. So, if that data were publicly available, it would really require there to be an international a scientific agency focus on the mid-latitude Mare regions, which we don't typically tend to see. It's mostly just the poles where the science missions go.
So basically what you're talking about now is that you have now a sort of a catalyst for a business model to now do your own mission to get that ground truth that you need. Or you mentioned in the first day also a desire to purchase higher resolution data, which in theory could come from an agency if any agency assets were able to produce that high resolution data, or you could get that privately. So I think that now I'm kind of answering my question a little bit. We've reached the point finally that we're at a tipping point where I think we're going to see a lot more activity happening before the next Space Resources Week. So I see Clive grinning down there, and so I'm wondering how...
He can't wait till
right,
the end.
He can't wait. How do we get this going more in a collaborative and international way that involves also the space agencies?
Okay, let's get real. We've got rovers, we've got Viper, we've got Lupex, there's the Rashid 3 UAE rover, there are other micro rovers, and they're totally uncoordinated in what they're trying to do. And we need a campaign, and if you don't have a campaign, a prospecting campaign of coordinated missions, doesn't matter where they come from. And Gary is exactly right. They're having to fund their own prospecting mission because the direct data aren't available. And what we can do as part of that campaign is to pull together through international collaborations, because it's expensive to do all these missions. We can do it with commercial collaborations as well. But there needs to be a coordinated prospecting campaign, and I'll keep using that word campaign, and we've got to get out of this mission mindset. It's not a mission, it's a campaign of missions, and we have to get that in order to make progress to get the ground truth data, in order to get to what Carlos Espejel said earlier on about we need to get to be able to say what the cutoff grades are. So that is when you can go to investors to give the credible data to them that they can then, you can then get backing to go mine the resource. But this is where we have to come together as an international community, not just space agencies, not just commercial, but we need to coordinate it so that we get the data efficiently and effectively and share it properly. So.
Right, yeah, sharing is something we're going to come back to in great detail about the data in particular. But Antonio, you're involved in the UN committees, and in terms of like supporting more international collaboration, do you see that in a positive light? Are there structures that exist or are being made that can be supportive of that?
Yeah, absolutely. Sorry, Abby, I know you wanted to jump in. But yes, so at the United Nations Committee on the Peaceful Use of Outer Space, there is a few initiatives that now have ramped up in the field of lunar activities. One of them is the Action Team on Lunar Activities consultation. It was established in 2024 after the first UN Lunar Conference that were organized by the UN Office for Outer Space Affairs, with a mandate to examine how do we improve consultation and hopefully also coordination of lunar activities. And I just came actually from an ATLAC meeting, that's why I just arrived in the room right before this panel, and there are now recommendations being prepared on potentially establishing an international lunar mechanism that could then be discussed and negotiated and created next year and potentially announced at a Unispace 4 conference. Then there is the UN Office for Outer Space Affairs has a project called One Moon for All. Through this project, essentially UNUSA gathers different stakeholders for high-level informal dialogues that can help inform the work of the diplomats and the policymakers to go into the right direction and to make sure that we can do this in an informed way. And that's going to happen through this lunar conference. So we did the first one in 2024. Then there was, last year, there was one on commercial lunar activities, where we brought a lot of the companies that are in the room here to talk about their needs and explain what do they need from the UN and how they can contribute. And this year, we're going to have a third lunar conference. It's going to be the biggest ever, 3 days, and we're going to focus on this international lunar mechanism, having space for member states to discuss, and then later on for civil society and industry to chime in. So I think there is a great framework in place. We are living really at a special moment in time to really make this happen in the right way, and I'm very positive, I have to say.
Yeah, that sounds very, very optimistic and positive. And so with Clive's initiative, sort of from the science and engineering side, coming together with some of the more policy-based initiatives, I think hopefully we can meet in the middle. You have a comment?
That's why I hang out with a lawyer.
Right.
Yeah.
I mean, we got Clive at the UN just a few times now, and they didn't kick him out, so that's already great.
It's also a positive sign.
Diplomat in training, yeah.
I think one of the big issues or differences of the past versus what Clive and others are talking about is if you look at the standard approach for, at least at NASA, with the CLIPS program, it run out of SMD. They have a PRISM call that's based on pursuing a particular science theme, and then you kind of prioritize different science themes. It's kind of one-off type of thing, and where we're talking about and why you're seeing Gary having to do his own mission is the pace of how we need to do this needs to increase. We can't just do this call once a year. Is it a science theme? It's got to be more focused. It's got to be more commercially driven. And the current, at least on the US side, was never really set up to do that. And it will be interesting to see how other space agencies react to that kind of an environment that, okay, science-driven exploration is good, but if we really want a permanent presence, we're going to have to think about the technologies, the resources, the infrastructure. So that's something that I think everyone on this panel is probably seeing, that we got to pick up the pace.
Right, and I think by this time next year, we're going to see something radically different. We'll have some additional stuff to discuss that's happened because of this new impetus from NASA's new program. So I want to kind of step back to, Clive mentioned data sets. I mean, we have a lot of data sets that are already available. And so, Abigail, I wanted to ask you about how you're having a new look at these data sets as you're working on this resource model, to give us a little perspective on, is there a lot of room for improvement on those existing data sets?
Yeah, I mean, I think that there is always room for improvement in everything. So yeah, no, I just want to point out that something that I think that is really important that Jerry said before is like, I mean, a few years ago, this conversation about data, it wouldn't be as, we wouldn't have an entire day of prospecting and exploration, an entire panel of data. And that is a big change because actually or at least it's my field, I've been in the Space Resource Week since the very, very beginning. And it's like, I see that it's a change. And it's a change and like things are getting serious. So I don't want to think it was the limitations. It's like, right now it's like, it seems that everybody took the sleeves up and it's like, okay, now we are going to work. And our data is like, we can improve in so many ways. We can improve in having more data with better resolutions, different type of instruments. We are relying on the instruments that we have, but we still need to explore different type of instruments that we haven't used on the moon before. Maybe there are new things, new techniques that allow us on the ground and orbital, in everything to improve that. And not just that, I mean, in the previous sessions, we saw many companies that are actually attacking the data set, attacking in a good way, from different perspectives, like using new tools for processing, automatization, the things. So that is really important because that will make us to do everything faster, in a more efficient manner, cheaper. And I think that that is a turning point that just a couple of years ago, it was impossible even to imagine. So I think that, as it was said, we are living in a really exciting moment, and things are getting serious now. I mean, and I always say, I make the joke, it's like when lawyers are in, it's because things are getting very, very serious.
One thing about data sets is, and this conference is shown it quite a bit, you're seeing a lot of really interesting instruments, and you're seeing a lot of very interesting mission concepts, but they're discrete. There's like a certain instrument on this vehicle at this altitude for this period of time, and how you pull all those data sets with different resolutions, with different altitudes or locations, different factors. That is also, I think, a critical aspect that, with Clive and the coordination, it makes sense now that if you can only fly one instrument in one orbiter, how does that fit into the bigger picture, making sure that it's done right? I think that falls into that category.
Yeah, just just we got to break the mold. We got to get out of the mission mindset. Okay, we know, for example, we take water ice, we know what we don't know, and we need to go know it. So if we're going to do a campaign, what do we equip 20 rovers with to go get the data from different locations? We know that. We've seen the instruments. It's bringing that together in a production line. Yes, it's going to be expensive, but if you do duplicate builds, you're going to save on the duplicate builds. So, and it requires the commitment from not just one space agency, but a collaboration between space agencies to be able to do that.
Right, and I'm wondering, Gary, if you could comment too about the interest of the commercial sector in maybe contributing to such a model.
Yes, absolutely. So, but first, before I follow that, I had a thought on the amount of data. There is a lot of data. It is primarily data of interest to answering scientific questions. But there is a dearth of data. There is more data needed if you are trying to approach it from the standpoint of resource utilization. For example, you can say there is a certain ice content that, in a particular location, but what is the actual form of that ice in the way that it could be, you can think of it in terms of extraction. Like if you're a mining company or a resource utilization company, you need different kinds of engineering data as well. In terms of your question of how we contribute, I mean, certainly you can't get around the fact that for a commercial company, there is a business model. You have to make money, right? So if you make an investment, certainly we want to abide by all data sharing provisions in international law, but in order for there to be a financial incentive to invest in extracting data that is, there has to be some level of protection. So I think from our standpoint, we would certainly love to share as much information as possible, but we also need to justify a return on investment, whether that is having tiered data releases or even embargo data releases over time is another mechanism. Wait 5 years and then it's publicly released.
Or lower resolution, It's like the satellite imaging. I'll give you the 5 meter per pixel map, but I'm holding the 1 centimeter per pixel map.
Exactly. I wanted to follow up, if I may, on a few of the points that we mentioned. So just the last one on data sharing, absolutely agree. And that's exactly what we are looking to discuss with ESRIC in the project that we're going to do on information sharing for resource prospecting. What are the solutions that will allow us to take into account legitimate commercial interest with the need to organize somehow how do we share the data, because it's also going to be in your interest to share it if others are going to do the same. And then the collective view of the data will be much bigger than the sum of its parts. So I think the tiered approach, the lower resolution, the embargo, there are all potential solutions that complemented together can deliver us where do we need to be.
Well, I think another aspect that a lot of people don't think about is the time of the data. Yeah. So, a typical science mission, the PI holds the data for a year and plays with it on their own before it's publicly released. Gary's going to hold his data until he gets a chance to sell it or some venture makes it worthwhile.
There will be a press release.
Yeah, there'll be a press release. So it's not just, am I collecting the data, it's how fast am I getting access to that data and using it.
Exactly. And another point of what Jerry mentioned before on the compatibility, right? So there are many data sets that exist already. That's what I'm learning from all of you guys. But it's difficult to put them together, right? Because they look at different resolution, different places. They've been taken with different instruments, different goals in mind. So I think at this point, someone needs to take the lead and set the standards on how do we collect the next data and how do we organize the data that exists already so that they make sense for reserve estimation. We have to have somewhere to find and someone to follow, and then the rest, I think, will compile it.
Right, so maybe Abigail, is that part of the motivation for the lunar resource model?
The main motivation for the lunar resource reference model is like the fact that we realize that most of the data are scattered through different repositories. They are, as for some people, are difficult to actually access to it. And the most important is like, I mean, experts know how to find the data, how to work with the data, but actually who make the decisions, they are not always the experts one. So actually we have to have a tool that allows to transform data and information into knowledge. So actually something that is easy for also the decision makers to look and understand. And it's believable, and a big part of actually this platform is not just provide the data, but also provide track of from where this data come from, what are the process that has been followed, who is responsible of the data. So actually you have somebody who says to blame if something is wrong, that probably, I hope everything is going to be fine. But actually you have track of the data, the uncertainty that is linked to that data, how much we trust that data. It's like, we cannot just be blind and say, oh, this is the real truth, no. And actually from that, then it's like when we can start to thinking how we can take, what it will be the next type of data that will help to decrease this uncertainty. What is the most efficient way to actually using our resources, our money, and our effort too. So that is the main part, actually. Make something accessible for everybody, even non-expert, to decide and to make decisions with knowledge.
And Clive, as a scientist, you can explain this better than I can as a non-scientist, but the thing that has surprised me tremendously over the years when we use the term data, okay, there's the raw data that comes from an instrument, and then how do you actually interpret that data based on previous models or Earth analogs or whatever the case may be. So I think you were alluding to that second level of data where it's already had some level of interpretation.
Well, let's think it through. Antonino started it with standards. How can we trust the data? And that's what the PI-led mission is supposed to do, and that's why they hold on to it, is they analyze it and they process it so that they can trust it and it can be put out there. There is going to have to be a streamlined way of doing that, but it requires standards to be adhered to. And I'm thinking, as you were speaking, Abigail, you just set up a really good session for next Space Resources Week about what are the next data sets and how do we integrate them with what we've already got for different resources. Because that then shines a spotlight on what we need. But within that is, how do we streamline the processing so we get credible data, usable data that can be integrated pretty much seamlessly without having to check it, massage it, reformat it. I mean, geophysics, if you want a different answer, let them reprocess it. I mean, and we don't want anything like that. We want to be able to understand the data. Any geophysicist in the room? I was being facetious, a little bit. But we need to move forward, but it needs to be in a coordinated way. It needs to be with a campaign mindset, and it needs to be with a laser focus on the next thing that is going to make a difference, not the next thing that's going to be a major scientific breakthrough, although I'd like that, but that's not where we are right now. So we need to get out of the mission mindset. This is exploration science, because it's going to be exploration-focused science in order to conduct exploration where the exploration-enabled science will get done and get done in abundance.
Yeah, so that kind of ties into something that we actually had discussed a little bit before offline here, which is, I mean, is there still a difference between science and resource exploration?
No.
No.
Well, I would say slightly differently. And again, as a non-scientist, I can make this joke. So early on, when I was working with scientists and resource exploration folks, it was kind of like the difference I saw in missions myself was a science mission may have a rover and it's going around and it looks for the things that are really unique. It's like, oh, that's really cool. I'm going to go over and take a measurement of that. Oh, that's really cool. Whereas if you're doing resource assessment, it's mostly plodding along, taking multiple samples, whether it looks cool or not. You're building that statistical data set. So a colleague of mine, Julie Kleinhens, led a study called LWIMS, and it's been published, where we had scientists and engineers and resource folks look at that question of what is applicable to resource exploration, what is science, and there was a bulk of things in the middle that, you know, were common. Now, there were unique science things, there were unique resource exploration things. So Clive is right for 80% of what we're doing, there's no difference. Slightly modification in terms of how you do it, the operations and the type of data and the amount of data you take. That's the key. To do what people have been talking about, resource evaluation and is it a reserve, the amount of data is staggering that you're going to have to take to do that.
And I think that's also now what's really exciting about the time right now is that the scientists and engineers and the venture capitalists and the commercial companies and everybody can get together now, and we're working on one major goal of learning some more about the moon. Right?
I have one quick comment. It's like it's really interesting because I'm agree with both, and it seems
it is hard to talk between Clive and I.
Yeah, no, it is counterintuitive, but actually it's like I think that is science, but at the same time maybe we have to reframe the way of thinking if science versus resources or whatever. Maybe what we should start thinking is like, what is the objective of this campaign or this mission or whatever, this strategy? What are the questions that I'm trying to resolve? And if we just go there, it's like, really doesn't matter if it's science or it's the thing. I mean, it's going to inform science always, that for sure, because more data is going to give us more information and more knowledge. But also we are doing it something very specific that requires a specific set of objectives and goals. So I think that is a little bit of both, and I don't like to choose, so I prefer like thinking in the mission objectives way of doing it.
So Gary, you'd like to...
Yeah, I think the key difference is that it's the same difference as what we call a resource and a reserve, right? A resource, you characterize what resources are there, but in order for it to become a reserve, you must prove, especially a proven reserve, you must prove that it can be extracted, right? And that involves a very different set of experiments and data. You actually have to have mechanisms for extracting it in an economical way. So both, as we move from science missions that are primarily characterizing resources into more exploration missions, we need to actually do engineering experiments too that are cracking the resource out of the regolith.
And I think given how expensive and technically challenging it is to go to the moon, we cannot afford to be exclusionary or binary, right? It doesn't have to be either or. Things and missions should be multi-purpose. To the extent possible, we need to incorporate science objectives, exploration objectives, purely commercial objectives in mission architectures that are integrated. Because we cannot just afford to do it one at a time. We have to go together.
I absolutely agree with that, but there are petabytes of orbital data from the moon. There is a lot of data there. And we can tweak it, we can get better resolution on neutron data around poles, but for some ground truth data, and if we can integrate those petabytes of data to show where to send those surface assets to look at 12 different places, then we start to get the statistics necessary at the granular level to calculate cutoff grades and reserves and so on and so forth. So it's going to be an integrated approach, but I come back, it has to be coordinated internationally because it's going to take the international community to do that, and that means the international commercial community to do that.
Okay, yeah, and one question I want to pose to both Antonio and Gary before we move to some questions from the audience is, what lessons can we learn from the terrestrial data ecosystem that we can now then start to apply to the lunar ecosystem?
Okay. There is a lot of lesson learned. So in the past couple of years, thanks to my friend and colleague Carlos Espejel from SpaceRS and previously iSpace, I've actually learned a lot about how terrestrial mining works. And the fact that we really need to look how things have been done there and not try to reinvent the wheel or to do it in a way that is completely unrealistic. And so one thing that I've learned is the standardization aspect. Again, you cannot expect an investor or a government or anybody who has some seriousness to believe just one company or just one actor without any validation from the community in the form of a standardized process. This is not going to work otherwise because, frankly, we're not stupid, right? We're not going to give you investment of millions or billions of dollars to do something that is unproven, that is not credible. I think what Clive said before about credibility is crucial. And the mining industry went through this process. I remember Carlos' presentation when he started with the idea of LORS, the Lunar Ore Reserve Standards. He talks about this accident where someone claimed that they had discovered a huge gold deposit, and it was all tampered data. It was all fake because there were no standards on how do you do prospecting. And someone had to jump off a helicopter, and people lost their money, and there was a huge scandal that could have destroyed the mining industry, and it still hampers its credibility. We don't want anybody jumping off a rocket on the way to the moon, certainly. So we're not going to repeat that mistake because nobody will let us do it anyways, right? So I think we need to learn in terms of the standardization and the regulation aspect. That's another element, right? The mining industry on Earth is heavily regulated. It's one of the most difficult activities in the world, and therefore it's one of the most governed. It's going to be similar to space mining. We'll start with less rules because we know less, but it cannot expect to do such an activity on a best guess case scenario, right? You will need to have rules because it's in the best interest of the miners themselves to protect their investment, to make sure that what we're doing holds up. So I think those are some of the key lessons learned.
Yeah, and I completely agree. Related to standardization, the point that is key for commercialization as well. Because, I mean, we are doing our own prospecting mission for helium-3 simply because we have no choice. But it would be much better to have international missions that have scientific standards, because at some point, without that, in order to do any large-scale resource utilization on the moon, will require a gigantic investment, billions and billions of dollars. At some point, like on Earth, that type of investment is done primarily through debt financing, through project financing. And you have the fact that there are standards. When you go to banks, you don't have to say, just trust us. This is going to work. The resource is there. Instead, if it could point to a scientific standard, peer-reviewed, and with enough scrutiny that those institutions, which are very risk-averse, they don't make their money with high upside equity returns. They make their money just on interest. And if the companies cannot pay that back because the reserves weren't really there, then they will not loan the money. So standardization, yes, I think is one of the key things we have learned from the terrestrial mining industry as well.
I would like to add one thing to that. Is like we are thinking about what lessons we can learn about the mining industry. That obviously a lot, but there is another industry that I want to take the attention that actually we can learn a lot. That is the terrestrial remote observation. So actually, these companies, many are commercial. They are having satellites all around. They are commercializing that data already. So I think that is also, we have a lot of things to learn from that industry as well.
Yeah, and to add to that, there was several conferences at the Ames Research Center dealing with off-world exploration, resource exploration. And one of the presentations really hit me. It was about government roles and resolution of data. It dealt with critical minerals. In the United States, Australia, and Canada were getting together to basically map critical minerals around the world at a certain resolution. And with the idea that you could then have anybody pick from that data set, and it was in a form that anybody could get into. And then that opened up the possibility of commercial companies going in detail for places to go. And so I joked about, Gary giving the 5-meter resolution and keeping the 1 centimeter. that kind of falls, you know, I could see government agencies buying that 5-meter resolution data early on just to publish that level and build this global data set.
I want to piggyback on what Abby said and also what Jerry said. The remote sensing industry is actually another great place to look at, as Abby said, because there are also principles there. There are remote sensing principles developed by the United Nations that say exactly what we're discussing here. So that if you are a country and you're being sensed by somebody else, you are entitled to the raw data. So again, not the final product, not the very, commercially developed one, but the raw data, yes. And that is a very well-developed industry from a commercial perspective. So it is the demonstration that you can have policies for data sharing that are open to everybody and still make money and still have an industry that flourishes and develops. So I think there is a lot that we can learn also from that experience.
Okay, thank you very much for the guided discussion here. I'd like to open up the floor now for questions from the audience. Back over there, do we have somebody who has microphones, or should I run
Anybody
around?
but Steve.
Okay, here we got up in the front.
Hi, Steve Freeland, and thank you. What a fantastic panel, and 5 people speaking unbelievable common sense. So I just wanted to share the experience that we're having, putting the principles together that I've spoken ad nauseum about. And you know, one of the essential things that everybody agrees, we have to share information, we have to share data. We reflect that in words, and then you immediately get the pushbacks. You immediately get the pushbacks in terms of, you know, to the extent feasible, practicable, if it doesn't impact on commercial and confidential, if it doesn't impact on national security, if it doesn't impact on our ability to be there first. So obviously we will find a way. We'll find a way in terms of trying to find the balance. But I look to you and I look to everybody in the audience. You know, what you're saying from all of your different perspectives is absolutely the way that we must move forward. Not just in resources, but space traffic management. You know, we're not going to have a system at all if we don't share information. And space traditionally has been this area where it's a needs to know and it's a competitive basis. And space resources, because of the geopolitics, is as much competitive, not just between commercial entities, but between groups of countries. Hopefully that'll change. So I look to you and I look to everybody to keep that message going. And how do you think is the most appropriate way to set a standard of sharing that is acceptable to competing and vested interests around the world? It's really an open question to everybody. Thank you.
Yeah, as Stephen was speaking, the hamster jumped in the wheel and started running pretty hard. So while he's in there running, I just wanted to say that we've talked, Antonino brought up the idea of standards. Standards is a very complex word, but it's something that's not insurmountable. And the other thing you mentioned, Antonino, there's another UN lunar conference, 3 days. And we need to talk about standards for prospecting data. Not the standards, get down to the nitty-gritty of standardization of this, that, and the other, but what are the levels that must be shared immediately once validated versus the levels that can remain proprietary for a given period? How long is that period? And we need to come up with something to iterate from. And that's the whole point, is to get a basis for discussion rather than nebulous discussions that go nowhere. And I think we can reach that, what you're talking about. But we need to broadcast it far and wide and get the input. And I hate to say this, but I've learned from Professor Freeland here, because this guy has the patience of about 20 saints. So, but we need to get people to push back on it, iterate it, make it better, but we need to have something to iterate from.
Yeah. Well, besides standards being a difficult term, data itself is a difficult term, because we've all talked about, you know, the quality and the quantity of data, the resolution of data. Is it commercially viable data versus non-commercially viable. There's lots of nuances there. So I can understand why you want to put nuances in there. But I think we have a lot of examples today in terms of, for example, Landsat. The US government puts out Landsat data and has done that, my God, for decades. But it's at a certain resolution that allows people to use it for certain things, but it's known not to be perfect to the resolution that somebody really might want to. And that opens up then the commercial market. So what you share, you could always share certain amounts of data, certain things. It's where do you draw the line in terms of intellectual property or that it is of business strategic value?
Yeah, two things. One, to Stephen's question, right? How do we set the standards? Again, here we don't have to reinvent the wheel. There are standards organizations in the world. There is the ISO, the International Standard Organization, which is now hopefully going to house the discussion on LORS, on the Lunar Oil Reserve Standards. That's going to be promoted by ILNAS, by ESRIC, by other standard organizations in the world. ISO has a very well-defined process to bring contributions from experts from all over the world, from institutions, from governments, from industry. So I think that will give us a house to discuss in the very technical aspects of the standards. It's also a very long process, and in the meantime, we can lead by example. I think we should not be afraid of getting these things wrong and therefore do nothing in the fear of, like, we are not doing the perfect example of it. And so, again, what we're trying to do with ESRIC, and I think what the campaign that Clive describes wants to do, what Interloon is also doing, is having a first attempt, right? And see, this is what we learned, this is how we've been doing it, and we can change it, and we're open for that. So that's what we call adaptive governance, right? The idea that we start with what is the most pressing need, with the information we have, the instruments we have. We give something to chew to the member states, to the rest of the community, and openly and intentionally we evolve it until it becomes good enough. And I think that's the only way we go about it. Otherwise, we will be sitting here for 20 years waiting to have the perfect solution, which will probably never come.
We're going to have to do some work, is what you're telling me. Yeah. That's my message.
Yeah, Clive, you can't retire yet.
Okay, do we have any other questions from the audience? It's your chance to ask.
I'm Alexander Lingle from Intel. It's a pleasure to be here. We were talking so much about data, and I was just curious about the standards of data, but there's also the other aspect. If you think of data as oil, as a metaphor, there's the refinement of the data and the pre-processing of the data that has to be done. What standards is being discussed as far as the processing of the data after the fact is collected? I'm just kind of curious what the panel has to say about that.
Yeah, we were discussing that last night at dinner about, okay, you've got all these data sets that are going to be integrated. How are we going to do that? What are the standards? And fortunately, we had Laszlo Kessler from USGS at the table, and he said, well, we've been thinking about that quite a bit, and we have a platform put together that is going to need some iteration, but we have something built that we can iterate from. And this is why virtual conferences don't work, because you don't have dinner with people, and you have those conversations, and you have those side conversations. Yes, we can have a panel discussion, but most of the aha moments will come out when we have coffee.
So again, I go back to data is not data. You know, there's multiple layers of data. So there's the raw data, then there's the, interpretation of data. And then there's the layering of data. There's been several presentations where, I take thermal data, neutron data, solar data, and how you overlap them. Some of that can be done in some of the models that are publicly available. Others companies are coming forward in doing that, just like on Earth. And what will really be interesting is if you're really interested in establishing a mine, it's not just where is the resource, but where do I set up my infrastructure? Where's my power? Where's my, logistics hubs and things like that? Those are very, highly tailored layers that, again, I foresee companies coming forward and doing something along those lines to support other businesses. So I think, again, it goes back to there's certain things that will be available to the public, and just like Earth observation data, there'll be companies that come out and say, hey, you got a problem, I can do the modeling for you. Or
Abigail. I have also, it's kind of a question also for my co-panelists, because talking about these multiple layers of data, we are, and just in the session before, we are seeing like a lot of people who are starting to use AI tools and machine learning to actually work with the data. And that also can bring some issues. For example, if you have commercial data, but you just release to some resolution, it's like actually with these new technologies, you can actually use super resolution techniques and things to actually improve it. So it's like cheating. So it's like, I think that kind of things also needs to be into account, that we are not just talking about maps and things, but also new technologies. And that this has been so complicated, I can imagine. So I want to ask to my co-panelists what they think about it as well.
Well, the one thing that I'm semi-excited about, so companies have come up to me and said, oh, I can show you where the ice is in this crater. I've developed the model. And, they have their techniques. Really, it goes back to the ground truthing again. And so in this LWIMS study that we talked about, as you gather the data, you increase the fidelity of your models and you check your models. Where did they correspond? Where did they miss? Oh, I'm going to get another data set to verify that. So that's my thought, is it's not one or the other, but it's going to be an iterative. And the faster we do this and the more integrated we do this, the better the models are going to be and the better the data interpretation.
Yeah, you're absolutely right. It's iteration of the model. I mean, an AI model is only as good as the data set that's in there, and the data sets that are in there, and we'll find limitations. And the beauty of AI is I'm an old fart, and I just trust I rather than A. So they do it faster. All right, they do it faster. So we can get to see the limitations of the data, and it puts a focus on those data that we need to get now, and we've now got a ramped up launch cadence. If we are prepared with our campaign, then we can go get those data and fill in those gaps a lot quicker. So that, to me, is the advantage of A, instead of just I, is that it does it quicker. And it allows us then to move a lot faster than we have done with the glacial science mission.
I want to add another point, which comes from what Clive said when he mentioned Laszlo and USGS, that on Earth, again, coming back to the lesson learned from terrestrial mining, the initial prospecting is done by public institutions, by geological survey. They conduct the missions, they get the data, they have the public maps. We don't currently have a lunar geological survey. Maybe one day we'll have one. But the question comes to, if we want to do these prospecting activities, if we want to do the maps, Clive said, USGS has the platform, we need to run it. How? We need funding. So that's another aspect that I think it's important to highlight. If we all agree this is important, that needs to go forward, we also need to gather some funding. And I think at the very early stages, we're not talking about huge amount of funding, but we do need to find and dedicate resources to do this properly. Otherwise, it will not get done, or it will get done cheating. As Abigail said, someone with AI goes and say, oh, I figured it out. And then we actually gonna go back to square one if we cannot trust this kind of processes.
Okay, so we're getting back to the final few minutes here, and we kind of got back to the data gaps and the ground truthing that we started at a while ago now. For the last round, I just would like everybody to say, what goal would you set for this community to achieve by next year? Or what do you expect to see achieved by next year?
Well, I'll actually let Clive start.
No, I'm not starting. I went first, but we started.
I mean, I'm both optimistic and pessimistic. I'm hoping that the messages that are coming out here from this panel and other activities reignites the idea of coordinating missions. And even if it's a one-on-one or more, I am very hopeful working with Antonio and Stephen, that some of the things that we do here go forward into UN languages. One thing that I was going to say is I think if we start establishing norms of how we do these missions and how we share the data, that alone will start helping things. So, you know, I try to be optimistic and see the things that are going around. And I think now being in Luxembourg, into a very international community, I am hoping to foster a lot more international efforts than I was ever able to do at NASA.
Yeah, and from the ground truthing perspective, we really are on the verge of a lot happening. So I think I would like to start seeing the real results from that. I hope we'll have much more data and to talk about at the next Space Resources Week. And I tend to feel that sometimes things, in terms of these questions that seem much more abstract and academic, they tend to start working themselves out when you're faced with the actual problem. I've seen this multiple times in my own career, and having worked reusable launch vehicles and commercial launch vehicle development, there was a lot of controversy around would it ever be possible or legal to commercially license a launch vehicle. And then all of a sudden people started just doing it, and the regulations and the norms and the practices had to follow. So I feel like what this industry really needs is to be faced with the actual real problem right in front of them of live data of, is it public? Is there a standard for it? How do we coordinate? A lot of that will start to happen when we have more and more missions flying and sending data back.
Well, lots of things we wish to accomplish on the legal and policy side by 2027. Actually, it's going to be like a turning year, hopefully a positive turning year, Stephen, right? For us. So I'll start with the ones that I'm in control with, which is the work we do at the Lunar Policy Platform. I'm really hoping in collaboration with ESRIC, we can come up with the first protocols and a sort of seed standards on information sharing for resource prospecting, at least mapping what is the legal landscape for it and what do we need to do to share information and what kind of guarantees we can put in place. Then beyond that, at the UN level, of course, hopefully by the next Space Resources Week, we'll have an agreed initial set of principles for endorsement at COPUOS, ideally at a Unispace conference. Same for ATLAC, discussions on an international lunar mechanism and how this will take place, whether it will also include some functions that are related to resource prospecting. And then, of course, from the UNUSA side, the Lunar Conference hopefully will provide yet another opportunity for what Jerry said, reconcile and close the loop between the technical discussion, the commercial discussions, and the policy-making discussion, which I think is critical because we all need to look at each other and make sure that we're still going in the same direction with an informed approach.
Okay, from my side, I just hope that next year we have better tools to actually inform the decision makers and also the general public about the importance of actually going to the moon and what we are going to do there on the moon. And I'm not very ambitious or very ambitious, I don't know how to take it, but actually I just hope that next year, we are closer to actually an international collaboration and prospecting campaign on the moon. That's my only hope.
Wow, I've got 13 seconds. No, we're beyond. I'm late. All right, I'll wrap it up. I'll wrap it up then. So next year, I would like to see integrated prospectivity maps for at least one area on the moon other than the Viper landing site. I think that's possible, but there's a dear colleague of mine once said there are two kinds of people in this world. There's those that go out there and make things happen, and those that sit there and just wonder, well, what just happened? And I hope that everybody in here will go out and try and make something happen in a very positive way in what we've been talking about. Come and talk to us and find out, if you're wondering how, is to come talk to us and let's go make something happen together, because it's a pivotal time where we stand, and I really think that the more positive inputs that we get to this process, I think then we'll be seeing great progress in just a year. But it's going to require effort from everybody. And as I say, don't wait for things to happen, but let's go out and make something really positive happen.
I was going to say one last thing from the
You always have to have the last one. You really are like that.
No,
From the
I get to
norms
have
and
the
the
last
legal
word.
aspect, I hope both Lunar Outpost and iSpace get the remainder of the money from NASA to transfer regolith.
That's a very specific goal, yes. And I'd like to also let everybody know, in terms of ground truth, by this time next year, when we're sitting here next year, the Chang'e 7 mission will have already landed on the moon, and we'll have results from another location near the South Pole about what is there in terms of volatiles. And so I'd like everybody to please thank the panel. We had an excellent time talking with you. And we won't keep you any longer from your coffee. So please come in and continue the discussion with us as you want to.
And thank you, Carolyn.
Yes. Exactly. Thank you, Caroline, so much.
Humanity is returning to the moon.